So, well, that's us, and I want to explain why electronics. I think you already gave a very nice example with your dark field, but you can do more. Just two examples of what you can do with our stuff, and it's actually working with the same firmware as you have it right now. But surprisingly, I wasn't really aware of that shipping electronics and hardware at the same time with versioning and all that stuff becomes that difficult. But nevertheless, let's take that journey and work on that. So what it can do, so I think the electronics you have in your hands has lots of output pins for the motors, for example, focusing different elements or laser turning on off, or also triggering cameras. Yet another example where you have fluorescence, where you have then two lasers and the LED array, what you're suffering with right now, and also then different steppers. So you can drive up to 4 steppers, 3 lasers, 1 LED array, and then control that through different ways like Wi-Fi, Bluetooth, and serial. And I must admit, I'm constantly programming, but I'm not keeping up with the documentation. So and also we switched during the last, I don't know, 2 months from the very old version to a new version. So bear with us. I'm trying to improve the documentation wherever I can. And yes, so just quick intro, so, because I had absolutely no clue how much you know about microcontrollers in general. So just quick dive in. So difference between this here and that one here. They look pretty much similar since it's all mounted on PCBs. But everything here on the left hand side, like the Arduino, this is a Teensy, that's a Raspberry Pi for Nano it's called? Pico it's called. And that's the ESP32, which you are also working with. They are so-called microcontroller units, or like MCUs, whereas this here is a single computer board, like SPB, I guess, SCB, which, like, what's the difference? Like, the computer runs an operating system, so you can, for example, run Python on the Raspberry Pi, and it can control cameras and have networking capabilities, and you have a GUI. I think even the ESP can also drive cameras and can even run Python, but it's much more contained, so it uses less energy, and also you don't have an operating system similar to what you're using with Windows right now. And so the major difference is like this chipset. So for example, like a typical CPU has, like, say, I don't know, 15 different chipsets. That means you can do floating point operations like multiplication, plus, minus, and stuff. So it's like very limited, but multiple, like the microprocessor in the microcontroller has even fewer so-called operation machine instructions. For the ESP, what you have in front of you is roughly summarized. So we use some of them, like, for example, what you see here on the left-hand side, that's a dedicated module inside this chip. So it's a system on a chip, SoC it's called, and we use, for example, the PWM. That's a dedicated chip that's running independent from this cycle. So microprocessor just means like that a process runs within a microsecond. So you have a loop that just runs continuously. And during the run, it, for example, asks for, like, the inputs, it sets outputs, it does computations, and it's very fast. So I think maybe nowadays it's not even micro, but even faster. And so in addition to the main processor, whereas the ESP even has 2 different cores, you have different registers and modules. For example, we can use the Wi-Fi that's running independent from the core, so that you can connect and use, for example, the WPS security features and stuff like that. And so for a device that just costs like €5, it's impressive what you can do with it. However, there are lots of things you can do wrong. So, for example, if you code in the wrong direction and you want to set something that's actually not existing, like you want to assign a port which is usually used for Wi-Fi, then the ESP automatically crashes and has boot loops, and maybe that's also something you already were suffering from. Nevertheless, there are chances to interact with the microcontroller. And so the code we deliver, I'm going to explain this in a bit more later, is open source, so you can download it and also then compile it so that it's understandable by the microcontroller by means of machine language, so it's compiling it in this hexadecimal blah blah blah, either in this platform IO. That's a very nice tool I recently discovered. It's also open source, purely running in Python, for example in this Visual Studio Code, or you use the Arduino IDE, which I think nowadays is quite nice but very limited. So but you just install the libraries, and that's just working, whereas this is a little bit more complicated. Anyway, yeah, so how did all that started? So we have the system, and we asked the community for help to at least get ideas how the whole thing should look like. And so we thought, hey, let's put the electronics in a cube. That was, again, very limited due to space. We had even some people designing stuff for us. But nowadays, what you have in front of you is essentially this here. So it's just a tiny board that has the ESP32 right here. So that's the board you have here in your hand. And you essentially lay out the different pins to, for example, drive the motors with the motor drivers here. So that's just a bipolar motor driver that's then connected here to the motor. And then you have some external outputs, like, for example, PWM for the lasers, the LED port for the NeoPixel array, or I2C, or some input pins, for example, to ask for end positions. And also you can hook up power LEDs that are amplified with this transistor. So that's pretty simple, so no magic there eventually. However, during the time we changed the layout a little bit because yeah, some pins were not optimal for high frequencies and stuff like that. So that caused the issue that now there are like 3 different versions of pins. So, and once you flash one wrong version, of course, the board won't work. So, but bear with us. I prepared something that should work out of the box. And just a glimpse, so that's something that's coming up soon, and then we are also done. We won't change the electronics and the software anymore. So this is like inspired by like the Game Boy slots that you can put in here, so everything becomes very modular, and also the firmware nowadays is very modular. Right, how to control it? So we have USB and Wi-Fi, and we thought it would be nice to have some standard that's already out there being implemented. So there's something called REST API that's usually used in websites. So whenever you want to get information from your from the internet, the browser sends an HTTP request, like either a GET or POST or maybe even a PUT request, and then you get an answer, so a return. And we wanted to follow the same structure because why implementing a new standard when there's already something around? And we followed that path. However, you are also able to interact with that, for example, with the PlayStation controller, since this uses Bluetooth, and the board, like the ESP, which comes in different flavors, also offers Bluetooth. So, for example, if you have one of those and you change the MAC address, so you have to, a bit hacky, then you can also control the motor and the LED panel, for example, with the PS4 controller. Yeah. So that's maybe also worth talking about briefly. So this is a board you can get off the shelf. So this is an Arduino. People from the CNC and 3D printer community have designed this board, which just, well, it's a shield for different stepper motors. And then people from the ESP community have designed something that looks like an Arduino, where you can then put on the shield on here so that you have a very simple and cheap way to use our code on an ESP. So what you were asking for is the LED. So oh, the codec is not available. Usually this should show a nice video, just so that you like a proof of that this is actually working. So I tested all of them. They should all work. And yeah, let's dive into the firmware. So if I'm too fast, just blame me for that. I wasn't quite sure how much I should talk about that stuff. So I was talking about the REST API. So that's something browsers use on a regular basis. But not only that, like, I think it's the most common standard in the internet, like TCP/IP, where you just have packages sending back and forth. And usually what you do is you have a so-called JSON string, or in Python it's a dictionary, where you have a key and the according value, and then you can just send it. And you can do that through Python, or you can do that through Serial, or through Wi-Fi, which is then pure HTTP. And something which is really nice from the ESP side is that it runs a web browser, a web server, where you can then, for example, change the different parameters without installing anything. So this is already implemented. It's not yet very nicely documented, so that's something I have to do. But yeah, this is coming soon. So this is a feature that's already there, but it's not yet documented. So I don't want to throw you in the very cold water there. So for a serial task, so when you want to, for example, move a motor and you don't want to install Python or anything, you can just go to, for example, your Arduino IDE. You open the serial monitor, and then you copy paste this construct here into the serial. And then what's happening here is, so the task is the so-called endpoint. So whenever you, for example, call or like access a website, and the endpoint is defined by, for example, google.com/ I don't know, shopping or something. Like the / shopping is the endpoint, so that the web server knows the routing. And we followed this structure. So this is the endpoint where the ESP knows, okay, I have to act on a motor. So if we just quickly go the next step, so you can also act on a LED array. So act means like an action. So you also have a get and a set. So this follows roughly the HTTP standard. So you can get information, for example, like the pin configuration, or set the pin configuration. And here, since we have 4 different motors, we have an array of, well, you can have up to 4 different motors. We just have one here where the stepper ID is 0. So A, X, Y, Z corresponds to 0, 1, 2, 3. And then you can set, for example, the position, the speed, whether it should go absolute or relative, or whether it should have an acceleration or not. And there are some more parameters which usually you don't need them. So that's one way of doing that for the LED array. We have different modes. For example, you can address individual LEDs, or like the full LED array, or just the left half or the right half. And in principle, you have to think of this here being a very long strip. So they are numbered. So it starts with, well, depending on how you count, 0, 1, 2, 3, 4, until 7. And then this here is 8, and then it goes to 15, and so on, so on, so. So it's a very long strip where when you think of, okay, I want to have a ring, you have to think of, okay, which number should I set to a value? The value is defined by red, green, blue. So then the ID is the ID of the LED starts with 0, goes to, in this case here, 63. And then you can either send, again, an array of lots of values, or you just do that sequentially. I think that's something we're going to do later. And then the last thing I'm just showing here as an example is the laser, which essentially accepts a pulse width modulated input signal or output signal, depends on what you want. So between 0 and 3.3 volts. That's also a bit special. In the ESP32, it doesn't use 5 volts, but 3.3. That's something you always have to keep in mind. And we have 3 different ports. So here it starts with 1. So if you want to start laser 1 with a laser value of 100, so this goes from 0 to 1024, then you can send this over the serial. So that's like the fundamentals, and then we have some more of the output and input modules. So for example, you can also read out sensors, you can actuate galvos and stuff like that, just as a summary. So, and the very last thing, so maybe to clear the clutter a little bit, so we have this firmware repository. This is now independent from the interface repository, so the one that you were asking for, I guess. And so what's happening now to make things a little bit easier, I hope on your end, this year, once we have a release, gets compiled automatically. So Jupyter has this nice feature of actions where you do continuous integration. And then once the firmware has been created, it's getting uploaded to a second repository, which hosts the website. And the website here is essentially doing nothing but connecting your ESP32 to the so-called web serial standard, and then you can flash the code. Alternatively, what you can do is you download or clone the repository and then compile it at home. So for example, if you want to add new modules or want to change pin configurations manually or something like that. Yeah, that's pretty much it for now. And so I also updated some of the documentation. So let's just go over. So what I was talking about now is the firmware repository. And this here is the repository for the interface. So maybe we have to also differentiate. So we have the firmware that's running on the ESP. We have the interface that's making a bridge between the ESP32 and Python. And then we have a GUI that's in our case called ImpSwitch. That's yet another repository that's having, well, a GUI for controlling the LED array, for example. And so what I created or updated today is this Jupyter Notebook. I just quickly posted in the chat. Maybe you've seen that already before. And we will just walk through it today. And what I said earlier, and there I think I would need your feedback quickly. So this is the website I was talking about, where you have your the ability to choose the different boards. In your case, it's that one. So you have UC2 standalone version number 2. The different port configuration here are listed here. Also, if you wanted to connect to a PlayStation 4, you would need to change the MAC address of the PlayStation 4 controller according to this number here. And yeah, so all the parameters, to confuse you even more, can be changed. So there's an interface in the ESP32 so that you can change the configuration. However, I think this is way too complex, so we decided now to pre-compile everything. And so what you do now, I'm doing now, sorry, my hair is just acting out. So I'm working on a MacBook, but the same thing works also on a Windows computer. Linux I haven't tested yet. So I have this board with banded pins, but it's the same as you have, just without the adapter board. So I'm connecting this here to the USB. So I'm connecting this here in my USB port because this weird.
I'm doing the same. I'm following what you're doing.
Cool. So when this happens, this thing here turns on. Ta-da! And I have connected the board here, in my case, to pin number 4, but in your case, it's a different pin number. So
it's from the bottom counted like the 4th, right?
I have to check. So physically, let's just quickly check. So it's number 32. So ESP32 pinout. So there are also many different variants, but what you have is the dev kit. So it's now connected to where is it? 32. 32, yes. So this is the pin number 32. And yeah, this is also maybe a nice summary of something we have to be aware of. So some pins can only do inputs, and some of the pins should never be used because they are used for booting up. So for example, 8, 7, 6, never touch those. Also these here, then the ESP is automatically crashing. It's a bit weird, but that's how it is. Right, and so the general walkthrough. So soon everything will also be even nicer, be documented here in this repository. Let's walk through. So you connected your ESP32 to USB, and you select your board. in my case, well, you select this here, I select this here.
Wait, we have to select the right one? Okay, yeah.
Yes, exactly. Yeah? And then there should be this window popping up. So this only works in Chrome and Microsoft Edge.
Do we have to click on connect first?
Mm-hmm.
Oh, yeah. Oh, yeah, I have to pop up.
Yes. And then you should see something like COM, because I think you're on Windows, right?
Yeah.
Yeah. So, and I hope you just see one COM port.
No, I see 3, but I know I put it in my COM5.
Nice. So we click here, and then, so you hit the install button, and then this takes roughly 2 minutes. Like with the flashing, yay, it worked. So that's good. I hope yours was also fine. Nice. So now we can go here to logs and console and check whether it's actually working. So what we type is like this open curly bracket means our task now is to get the state. So if I hit enter, okay, that worked. So
I have a
and so now you have 2 different scenarios. So you can install Jupyter. So what I'm doing now is I create -n UC2 test. And then, so I'm just creating a new Python environment saying Python 3.9. And then we install Jupyter Notebook and use the commands listed here so that everything should work also on your end, hopefully. Be done now. So we will now conda activate UC2 test and install Jupyter. Okay, this can be tricky. Let's hope, because my computer does not have this typical x6086 framework. It's a bit different. Sometimes stuff is not getting installed properly on Python. That's not your issue.
I'm not doing these steps now, what you're doing,
no,
right?
No. So I'm just,
okay.
Yeah, so now we're just starting a Jupyter Notebook. So that's also listed in the documentation. So depending on how you installed, sorry, now it's getting a bit messy. So let's just quickly go through. So the Jupyter Notebook, once you have it working, yeah, I tried to segment that into the different parts of the functionality. So for example, so like what you did in the browser, where you send the JSON string to get information or to set information, this can also be done with this Python interface easily. So you just formulate what you want to have. For example, like this state get. That's what we did in the browser. Is getting sent, and then you read out the return. And the return here is again, maybe I'm just doing that now. So that's exactly what you also saw in the browser. And so the dictionary can be accessed with the correct key. So that means the identified date is listed here, and that's when it got compiled. So last night, almost before midnight, it was compiled in the cloud, and then now you have it on your board. Like yours might be a little later, and also what I said. So you have different modules, which. That's something, doesn't matter so much, but you can activate them. So for example, you have an LED module for motors, spatial light modulator and stuff like that. And to not overwhelm the code or like the cycle run, you can activate and deactivate it. So for example, if you have Wi-Fi turned on, then also the web server is turned on, and then the motor have a reduced speed. That's because it's also getting so when the cycle of the microcontroller runs, it has to go through motor, through Wi-Fi, through analog pin and stuff like that, and then it's slowing down. So you can just speed it up if you deselect the different modules, and that's like this part here. Moving the motor, so in your case you only have number, or like the Z. So I well, we don't need to touch these settings anymore since your configuration should be all right. And then, so the moving part is like here, moving the motor. So I don't have a motor connected to this here, but we can also test that if you want. So you can move a motor with a dedicated number of steps, like 10,000, with a speed of up to 20,000 steps per minute, I guess. And then you can do that in a blocking fashion or in a non-blocking fashion. That means, so the function call waits for the return. So for example, here it's blocking. So when I run this, the next function is only run when this is done. If this is false, then it just sends the command to start running for 1,000 steps and the speed, but it will automatically continue to the next function here. And then you have also the absolute key, where you then can decide whether you want to go relative from the position where you are, then it's false, or absolute to a position where you want to go, and then it's correct. Yeah, like true. And yeah, here this is just for scanning, but in your case that's not so important. What's more important is this here. So what's yeah, so the evidence, it works on my end at least. So what this pin, this cell is doing? So first it asks for the pin, so the LED get underscore LED pin. That's just one function that's helpful for you. And then it sends a command to set the full LED matrix on, or like to a certain value. So in our case, that's 255, 255, 255, and then okay, cool. And so then the next cell, that's just for fun, but that's what you want to have in the end. So this is addressing random patterns periodically. So I think 10 or so, we can have more, like say 100. So as fast as it can. So it has a limitation. So what you see here now, so it continuously sends like these JSON strings with, I think 64 values, because here it's falsely set to 64. So 64 values times 2 to the power of 8 gray values times 3, so that you have just an imagination of how many data is now sent to the ESP. It waits until it says I'm done, because it takes a time to also flash it here, and then it continues. So this is what you want to have. So for example, I think the next cell here is then trying to address the left and right half. And so essentially what you do, either you do that by math or just counting the LED IDs. So for example, well, I should have indicated like what's 0, like LED 0. So let's try out, or let's find out how LED 0 is addressed. Sorry. So we just insert a new cell, and what we do is like we take this function and say, okay, LED pattern single. Yeah, we want to have LED index 0, intensity fully on, and the rest off. So what you then do is you copy the other function here. So you first set off everything, and then you...
Okay, maybe put this also in the chat.
Sure. So this is now the center LED. So it's a spiral going from center to the outside. You can do, well, a spiral night rider. So we do a while loop, while true, and then we set off everything. Then we go here, so we say for E LED in range 25, and then you just say, sorry, E LED. Thank you. And so what you see now, okay, that's funny. It's like this here. Do you see that?
Oh, yeah.
And then you see like the numbering. So 1, 2, 3, 4, 5, 6, 7, 8, and then it's until 25. so when you want to do dark field, you want to have a circle. So we create a new cell and say list ring outer. Say can do that programmatically, but we are lazy now, so it's what did I say, 16 values, or was it 12? 16, right? So we start with 9 10 11 12 13 14 15 16. So, is that true? 16, no, sorry, 17 18 19 20 21 22 23 24. So, and then we set these values to 1 and then send this pattern, and we don't want to switch it off. Ta-da! Oh yeah, of course it's red now because we only sent 1 value, so we can also do this here. Oh no, sorry. Missed my mistake. So it's expecting 3 values. So ta-da!
Cool.
So I'm now like this. What's it called? Iron Man. So and
Good that you say so. Otherwise, we would have thought that, of course.
yeah. So, but you can also change the numerical aperture, for example. So, say this here. How many is it? So it can be only from 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. Oops. Okay, that's bad programming practice. Usually you should do that better. So we reset the pattern. We set the pattern again with now the middle layer. It's really bright. So we do only the blue. So it's RGB 0, 1, 2. So we set that, and then we address that, and we move the 0. So, ta-da! And so because we're cool, we do that also for the 0 thing. Yeah, so this is a bit of an overkill because we know that it's only 1 LED, but just for brevity. So that's it. And because we are even cooler, we do again a for loop. And because it's Christmas, we can do flashy colors. So we do green. No, we start with red. We start with green, and then it's blue. Okay, blue is only 1 pixel, but it's fine. And then we add the time sleep for 1 second or so. Let's make it 0.1. Then it's a bit more flashy. So I made a mistake. What is it? This, okay, typo, classic. So you see.
Cool.
Yay. Okay, so now you can do stuff. So I'm not sure how much you could have followed this whole process.
Yeah.